So there's two aspects of momentum. There's linear momentum and there's angular momentum, okay? So we'll finish with the linear momentum part of it. So today we're going to cross over into angular motion, because you got to get angular motion before you can do angular momentum, okay? So there's a couple of things that are different when you begin to describe things that spin. So you have to be able to deal with some different scenarios. So one option is that I have this thing spinning, but it's not moving anywhere, okay? So I can have angular motion without linear motion. But I can also have angular motion with linear motion. How do we describe that? Now, the other thing that happens, as Vanessa demonstrated, when things spin, they do different things. So if I just hold this up like this, okay, and let go of it, it does exactly what you would expect it to do. But if I get it spinning, okay, and then hold it up, then it stays up like this. And if I take that and spin it in the opposite direction, oddly enough, it goes round in the opposite direction, but still stays up. So that's the things that we have to be able to account for. And then, if I lay it like this, then it basically turns into a big, massive spinning top. But if I stop it, and then do that, it just goes doink. So we have to be able to account and explain for all of that happens. So one of the big things that happens is that by the time the angular physicists really got involved in the game, all the good letters had already been taken, okay? So like the linear guys had taken velocity, okay, there's that, right? And they had A for acceleration, and that was kind of boring. And they had like D for distance, okay? So the angular physicists were going, what do we have left? They said, oh, you kind of got the Greek alphabet. They said, okay, we'll delve into the Greek alphabet. So when you describe angular motion, there's three Greek letters that you're going to use a lot. Theta, omega, and alpha, okay? Now, so you need to pass.
Whipping it out. The M&Ms. The M&Ms. Pause.
So here's the Greek letter theta. Omega and alpha. Now, let's just get, this is technically usually drawn more like that, okay? So let's just get this out of the way, because otherwise you're going to think you're the first person in the history of the world to make this observation. Yes, it looks like a butt, okay? Get over it. So let's just get that out.
I was going to say W, but okay.
And this looks like a fish, so generally it's theta butt fish. Louis?
I thought omega was the one that had like the little like square angle.
There's uppercase and lowercase.
Oh, okay.
Just like these are lowercase.
Okay.
Those are uppercase. Okay? All right. So here's the deal. So just like you have distance, that's going to be measured in meters. Velocity is in meters per second, and acceleration is in meters per second squared. Okay? So the same thing is going to happen here. But here's the problem, is that how do we describe that motion when it's just spinning, but it's not going anywhere? Okay, so we really can't talk about distance because, how do you describe that? Because like the distance traveled, if you're closer to the center, is going to be different than the distance if you're traveling out here, and it's just going to get awkward. So when you talk about angular motion, we use the concept of radians. Now, radians they're kind of this weird anomaly. It's the only time we'll ever talk about something that's called a dimensionless number. So when you talk about radians, that's just it. It isn't like radian meters. So if I say I went 5, well, 5 what? 5 meters, 5 feet, 5 centimeters. But if I say I traveled through 5 radians, that's it. There's nothing that goes on the end. So for those of you that are math nerds, if the tire completes 1 revolution, does anybody remember how many radians that is?
2 pi.
2 pi. So that's the most important conversion that you need to remember out of this unit. That 1 revolution is 2 pi radians. Now, there's some things that are important about this. So here I've got this bicycle wheel, and so I've got like this little piece of tape right here. So if that piece of tape goes all the way from here to here, that was 1 revolution. So that's going to move through 2 pi radians. I don't have to say 2 pi radian meters, okay? It's just 2 pi radians. Now, here's the cool thing about this. If I move that piece of tape here, and it goes through 1 revolution, how many radians would it move through?
2 pi.
2 pi. If here's our star, and here's the Earth, and the Earth goes through 1 complete revolution, how many radians does the Earth move through? 2 pi. So notice that
2 pi.
radius is not a factor in this conversion. So one of the things that you'll see as we go through this is that a lot of times radius is a factor, but there are other times where it's not a factor. So this conversion from revolutions to radians is not dependent upon a radius, okay? 1 revolution is 2 pi radians, doesn't make any difference, okay? Solar system, Milky Way galaxy, an electron moving around the nucleus. 1 revolution is always going to be 2 pi radians. Now, just like I could walk pretty slowly, or I could walk quickly, or I could travel at the speed of light. The same thing is going to happen with object spin. Sometimes things spin really slowly, okay? And that's a certain number of radians per.
You gotta pre-write them.
I was on such a roll too.
I mean, you can.
Now you gotta
pick up
restart
where
the
you left
lecture.
off.
You gotta rebuild the momentum.
Okay,
Done on velocity.
Rebuild the radius.
so sometimes things spin slow, sometimes things spin fast.
Fine.
So just like meters per second is a reflection, it's a rate function. It's how many meters per second that you're traveling. So a rate function in terms of how fast things spin, instead of meters per second, it's going to be in
Radians.
radians per second.
Yeah.
Okay? So here's the deal. So distance in your normal system is measured in meters. So theta is going to be how far it moves in a circular path, and that's going to be in radians. So just like velocity is meters per second, omega is radians per second. Okay? Cool with this.
Cool.
Now, just like acceleration is meters per,
Section squared.
and the easiest way to calculate that is change in velocity over time. Guess what alpha is going to be in?
Radians per second squared.
Radians per second squared, and the simplest way that's going to calculate that is going to be
Radians over.
delta butt over time. It's the rate at which your butt changes. Okay, that's it.
Quite
Sure.
a lot, then.
What'd you say?
Say quite a lot, then.
Okay, all right. I don't need to know that. That's borderline biology. Okay?
Yeah.
Now, so, and the same rules apply. If I just hold this thing like this, okay, and don't apply a force to it, what's going to happen?
It's gonna do nothing.
It's going to stay at rest, right? Okay? So the same thing is true with angular motion. An object at rest is going to remain at rest until
Now it's like.
an outside force acts upon it. So then when I get it spinning, guess what? It's going to keep spinning until
An outside force.
an outside force acts upon it, and then it's going to
Stall.
slow down. Okay? So just like the same thing is going to happen. If you look at an omega versus time graph, so this, if I start this wheel off at 0, and I make it speed up, okay, I have to apply a force to it. I have to change the angular velocity. So I'm going to make it speed up for a while, and then it's going to spin at a constant rate. So what's that graph going to do? While it's spinning at a constant rate,
It's gonna increase linearly.
going to what?
It's gonna do nothing. It's gonna remain constant.
It's going to be a horizontal line, right?
Got it.
And guess what? It will maintain a horizontal line until what? Until an outside force acts upon it, and then it's going to slow down. Now, what if I slow it down and make it go in the opposite direction?
Goes past 0.
Yeah, then it's going to go past 0, and
You have negative butts.
yeah, then I got negative butt, and then a constant butt, and then there. Now, the same thing applies. What do you think was going to happen if I find the area underneath my butt time graph?
I'm gonna get alpha, but
Huh?
Oh,
You're
it's
gonna
just
get
radians.
alpha.
It's
I'm
just
gonna,
radians.
now I'm going to get alpha.
You're gonna get theta.
I'm going to get theta.
oh,
Why?
shoot.
Because it's radians over seconds, and if you multiply by seconds.
Yeah, so this
You're
is radians per second
I looked
times
up, I didn't even know
seconds. The seconds cancel out. I get
that. Radians.
radians, which is going to be a reflection of
Theta.
theta. Now, the slope is going to represent,
Yeah.
the slope is going to represent my acceleration. Okay? So it's the same ideas. Okay? A is going to keep moving until an outside force acts upon it. Okay?
So
If you have positive alpha and positive omega, what are you going to be doing?
Increasing.
Yeah, you're going to be speeding up. If you have positive omega and negative acceleration, you're going to
Slow down.
slow down. Same rules apply. Okay, we're just going to make things spin. Now, where things get a little complicated is when you have both. When you have angular velocity and linear velocity at the same time. Okay, that's where it gets a little bit complicated, but it's not bad if you think it through. So there's three what we call crossover equations. D equals R theta, V equals R omega, and A equals R fish. Okay? Now notice that what do all three of those have in common?
They all have radians.
Radians.
They all involve radius. Okay? They all involve a radius. Now here's what I want you to look at. Okay? So I want to start with a simple example. So let's say that the radius of this bicycle tire is 0.25 meters, which it is. Okay? So the distance from here to here is 0.25 meters. Now, here's what I want you to think through. I'm going to take this wheel, and I've got this piece of tape here at the bottom. Okay? And I'm going to have it here, and I'm going to roll this thing until that piece of tape gets back to the bottom. So what I want to know is how far did the wheel travel during the time that that piece of tape went from the bottom back to the bottom.
0.5. 0.5. 'Cause
So half a meter
yeah,
diameter.
yeah. Because isn't it radius time or
The circumference of the wheel, right?
Why the circumference?
Because the distance or rotating, or the distance around the entire wheel is the circumference, and if it's rotating until it's traveled all the way around,
Yeah,
it would have traveled the circumference.
you're right. So Louis, imagine this.
yeah.
Imagine that I'm going to take this piece of string, okay,
Uh-huh.
and I'm going to wrap it around the wheel, and let's say it went all the way around, okay? Imagine this goes all the way around.
Yeah.
So then if I took that and then stretched that out straight,
It would match the length of the.
it would match how far the wheel rolled.
Yeah.
Okay.
I was plugging in 2 pi for d equals r theta, which is just 2 pi r.
Yeah, we'll get there.
So gotcha. Sorry.
You're to step 3. I want to do step 2 first, okay? Now, so here's the
Yeah,
deal.
man. Arc length.
So, if we look at just the circumference of the wheel,
Oh,
Two
dear God.
passes.
Don't you dare ask for one, Mason. Ah, dang it. Sam.
Sam's not here. There you go. He had to.
Sam's failing physics.
I'm failing physics.
Was it easy? It's a lot of math.
It's every test.
It's
Okay.
not too bad. It just takes.
so here's what, if we're going to find the circumference of the wheel, right?
Right.
Circumference of the wheel is 2 pi r. So if we're just going old school circumference, okay? That's going to be 2 pi times 0.25 meters. Cool? Now, this is where I deviate from the math nerds. Okay? The math nerds are going to say, you need to leave that in terms of pi because that's a more precise answer. And they're right. Not disputing that. Okay? Not disputing that at all. But here's the problem. We don't have meter sticks that measure in units of pi. We have meter sticks that measures in decimals. So that's what we have to work off of. So when you're doing these, I know mathematically you want to sit there and go, oh, that's 2 pi. 0.25 is the same as 1/4, and that's pi over 2, and we're going to travel pi over 2 meters. Cool. Legitimately, we are. Try and measure pi over 2 on a meter stick. Okay?
Done.
It ain't gonna happen. So when you do these, you have to get beyond this, oh, I gotta leave it in terms of pi. You can't, because we're not gonna measure it in terms of pi, we're gonna measure it as a decimal, okay? So somebody basically run the numbers, take pi and divide it by,
1.57.
what'd you get?
1.565.
1.5.
That's his brain.
That's me guessing. What is it?
1.57.
Oh,
1.57 meters.
same thing as 565.
Okay? So that's the distance that wheel is going to travel. Now, a little comparison. We're going to take Gary the golf ball. Okay? I'm going to take Gary the golf ball. And I'm going to have Gary the golf ball roll through one revolution. What's the same and what is vastly different?
The angle and the radius.
Different.
What'd you say, Jackson?
The radius is different.
The radius is different, but what's the same?
2 pi.
It's still going to travel through one revolution, right? Now, so here's the deal. So this is old school, okay? It's going to travel the circumference. You go, oh, but Burkamp, we're new school, right? Let's use the new equations. Oh, okay.
No.
Well, that's D equals R theta, which would be 0.25 meters times how many radians did it move through? 2 pi, right?
Yeah.
So oddly enough, you're going to get the exact same answer. Whether you think of it in terms of here's the circumference, or you go linear distance, you need to pass. Okay. So yeah, so whether you want to go old school circumference or go new school with this, you're going to get the same answer. This is actually a slightly deeper truth that you will that can actually that allow you to see different things. So if I take the golf ball and roll it, that's still going to travel through one revolution. It's still going to travel through 2 pi radians. But obviously this is going to have a much smaller radius. So the linear distance that it travels is going to be much smaller. Now here's the anomaly. D equals R theta is a linear function. You go, no, it's not. Sure it is. Okay? So we're going to put distance here, and we're going to put theta here. So we could do like 2 pi, and then we could do 4 pi, okay? Obviously this is going to start at 0, 0, right? So we said if the radius was 0.25 meters, right? That traveled 1.57 meters. So in one revolution,
3.1 square.
Do you want this just in the?
yeah. So here's the deal. If we went through 2 pi radians with the wheel, we traveled 1.57 meters, right? Okay. Went through 2 pi or 4 pi, oddly enough, we travel through 3.14. Have a line like this. Now, out of curiosity, let's find, could we find the slope of this line?
Yes.
Yes. So somebody take 1.57 meters minus 0 divided by 2 pi. Now, let me give you a word of caution. When you divide by 2 pi, you have to put those 2 pi in brackets.
0.25.
Because if you just put divide by 2 and pi, it's going to divide by 2 and then it's going to multiply by pi.
Even if you put 2 pi without
Oh,
a
0.0.
multiplication.
No, some of it will flip out.
Okay.
0.249.
What'd you get?
0.25.
Oh, what'd you get? 0.25.
Yeah.
Oh. The slope of the line then is
The radius.
0.25 meters. So this is why this is a linear function.
Wow.
Okay? Doesn't look like it, but it's a linear function. Now, knowing that the slope of this line represents the radius, what would that line look like for the golf ball?
One pointing straight up from the center. Because the radius is the center to the outside.
If we drew this graph,
Yeah. Oh.
It would be the same.
or would it be the exact same? Would it be more steep, or would it be less steep?
If you did what?
If I drew this graph of distance traveled versus theta for Gary the golf ball,
Oh, I
If you
thought we
change
did.
your
Okay,
units,
yeah.
it'd be the same.
It'd be smaller
why?
because the radius is super small.
Yeah.
I thought that was the golf ball first.
No, that was the bicycle.
Yeah.
That's one big honking golf ball. Okay? No, this is the bicycle wheel, right? So think about this. When this goes through 2 pi radians, what do you know about the linear distance? It's going to be much less. So, and the radius is also going to represent the slope. So that would be the golf ball. Okay. Now, what about the Earth?
It's gonna
It'd
be
be a lot
way
steeper.
See, really steep line, right?
Yeah.
Okay, because in one revolution, you're going to travel a much greater distance. Okay, but here's what I want you to focus on. If you look at the radians, that is not dependent upon the radius itself. Whether I'm a golf ball going through one revolution, whether I'm a bicycle going through one revolution, whether I'm the Earth, that's still going to be 2 pi radians. What changes is the linear distance it's going to travel as it rolls. Okay? Makes sense. Okay. Now, let's talk about V equals R omega. Okay? Now, every time you have driven your car, you have used this equation. You know you not, okay? We've never seen this equation before in our entire life. Let me give you a quick lesson in auto mechanics, okay? So here's your drive tires, front or back, depending upon the situation, okay? And that's hooked up to some source of power, okay? Somehow hooked up to your engine, either directly or through a drivetrain, okay? And oddly enough, your engine makes the tires turn, okay? That's what it does. Now, so when you look at your speedometer, what your speedometer is showing you is the linear velocity that your car has based upon the size of the tires. So if you open up your driver's side door, there should be like a little plaque or panel or something like that, that's going to tell you the size of the tires, typically like R15, something like that. So your speedometer is calibrated based upon a certain size tire. So basically what happens is this. Somewhere, either an electronic or a mechanical sensor senses how fast something inside the engine or the drivetrain is spinning. So basically, that system measures omega. It's how fast something is spinning. Yes?
So, so the speedometer is made for a specific size of tire. So if my speedometer is off by 10 miles an hour, the tire size is off?
Yep.
Yeah.
Great.
Okay.
10 mile. Whoa, that means you have a really big difference, though.
Hold on, we'll get there. We'll get there. We'll get there. Okay.
Guys, going crazy.
So,
10 mile an hour is crazy.
your sensor is picking up how fast something inside that mechanism is spinning. And then it's basically based upon a certain size tire, which translates to a linear velocity. Okay? So that's why I said every time you've driven, you've taken advantage of this equation. You just don't know that you have. Okay? Now, this typically, and this, you don't see it as often as you used to. It's kind of become out of vogue. But it used to be, and it was typically guys that would do this. And they would typically buy like small four-wheel drive pickups. And they would put big oversized tires on it. Okay? So if that happens, here's what I want you to think through. If you put big oversized tires on there, okay, and you're calibrated based upon a certain size radius, are you going faster than what the speedometer is showing, or are you going slower than what the speedometer is showing?
Faster.
Faster.
Yes. Because for each revolution, you're traveling a greater distance than what that calibrated for. So if you do put on oversized tires, some people like that, you just have to realize that if you get pulled over and the cop says, hey, you're going 10 miles an hour faster than the speed limit, and you go, I was driving the speed limit as based upon my speedometer. And the cop's going to go, you have big oversized tires. And he's going to go, did you go to Mays High School? And you go, yes. And you go, didn't Mr. Burkamp teach you that? And if you say no, I will roll you under the bus. I will personally go to court and testify against you. So no. We worked through this example. Skippy just didn't pay any attention. Now, here's the other side of it.
I thought about doing it multiple times.
Let's say you're going through the rebel phase, okay? And I'm breaking the law, right?
Yeah.
And you think you have to drive faster than the speed limit because you think that's cool, right? And you're racking up speeding tickets, like none other. Your parents are about to kill you, your insurance company's about to drop you, but you're still in your rebel phase. You still want to look cool. So what can you do to the size of the tires, but you think you're speeding, but in reality you're not?
Make them small.
Make them smaller. You go out and you buy some little lawnmower tires. And you put those on the car. And then your friends can sit in the back going, man, you're cool. You're driving 40 and a 30. You're breaking the law. Stick it to the man, right? In reality, you're going about 25. Okay? So you can have the appearance of speeding, but in reality, you're not. Okay? Cool with that. So that's why I said every time you've driven, you've used that equation. And you're going, yeah, you have. You just don't know that you have. And then you have the same thing, A equals R alpha. Okay? Now, let's talk terminology. Okay? When you get into angular motion, you've got to be solid on the vocabulary. So let's look at a couple of different situations. I'm going to get this thing spinning. Okay? Which point has the greater angular velocity in radians per second? A point closer to the center, or a point further to the outside, or is it the same? Why is it the same, Jackson?
Because they're both traveling one revolution.
They're both traveling the same number of radians, right? And they're both traveling that in the same amount of time.
Yes.
Right? It's going to take the same amount of time. If you timed each one of those, it's going to take the same amount of time. So if you have a spinning wheel, okay, every point on there is going to have the same omega. Now, here's the deal. What's the only time you can calculate velocity by taking distance and dividing it by time?
Constant.
Constant velocity. The same thing is going to be true of angular velocity. The only time you can calculate angular velocity by taking theta and dividing it by time is if something is spinning at a constant rate of spin. Like the Earth, for example. The Earth is spinning at a pretty constant rate of spin, thank God. Okay? It's technically slowing down a little bit, but don't worry about it. You can talk about the moon.
It's what?
The Earth is actually slowing down.
Is that like a big issue or like not really?
It will be when.
It will be eventually, but don't worry about it for now.
We'll be dead.
This
by
is
then.
why you have to, this is why every once in a while they have to adjust the clocks, because the Earth is slowing down. Just like a top slows down, Earth is gonna slow down. They
So
think
we'll
the
have
Earth
longer days
Yeah.
and longer nights.
Awesome.
That would be so cool.
So we'd have to like add an
or
extra.
hot, depending upon which side you're on.
Yeah.
I don't
Wait,
know.
wait, wait. So
if
so would we have to add more time, or would we extend
Eventually,
the
yes.
second?
Or we're going to do something.
But would that be in like?
It won't be in our life.
Thousands
It
of
won't be
years?
in. No.
No, it's,
No.
I think it'd be fun.
But every once in a while, they do have to adjust the atomic clocks because of that. Okay? They do think initially, many, many years ago, the Earth was actually spinning about twice as fast as it was right now.
Wow.
So instead of a day being 24 hours, a day was 12 hours long.
That would suck.
Yeah. So, okay. Right. 7 days of the week, whoo, 14, there we go. All right. But again, there's so many other things to worry about. We're going to screw that up. We're going to screw this thing up way before we get to that point, so don't worry about it. And the sun's going to get bigger, and we're going to turn into a red giant and all this other stuff. But again, don't worry about it.
By that time,
Okay. So here's what I want you to see,
Well, we never thought of it.
is that this calculation here is not dependent upon radius. So angular velocity, when I talk about angular velocity, I'm talking about radians per second, not dependent upon where you are on the wheel, okay?
Okay.
Now, if you talk about linear, and sometimes you'll see it called tangential velocity, okay?
What a word.
Then that's when you're talking about V equals R omega. So there's a couple of ways you can think about this. So as this wheel spins around, imagine that you had like a little radar gun, okay? And you could shoot the speed, notice I said speed, at this point or a point further out on the outside. Would both points have the same speed if you were shooting it with a radar gun?
No,
Louis, which one would have the greater speed?
the farther one,
Why?
because it's having to travel a further distance in a shorter amount of time, or in the same amount of time.
Same amount of time, okay? So this wheel out, this point out here has to travel a greater distance in the same amount of time as the point here. So that's one way you can think about this. Some people like to think of it, if you were like in the band, if you're out here and you're trying to march around in a straight line, if you're out here, you've got to walk much faster than you do if you're closer to the center. That's how some people like to think about it. So I don't care how you view it, but here's what I want you to see, is that when you're talking about tangential or linear velocity, that's dependent upon radius. Angular velocity is not, okay?
What does tangential mean?
Tangential just means like if you were shooting the radar gun like at a tangent,
Oh, okay.
like here's my finger coming around like that, and you would shoot that radar gun like out a tangent as that comes around,
Okay.
okay?
Yeah.
Got that?
Gotcha.
Okay. Now, we got one more big topic to talk about. And this is another thing that you have dealt with every day of your life, you just don't know it.
Dang, Connor, the camera's not on.
It is on.
Oh, thank God. Don't scare me like that, Lily. Seriously, do not scare me like that. Because I'm going to say, sorry, boys, you're on your own. Should have been here,
Here's the paper.
okay?
Good job on state, but you're in the wrong school.
Huh?
You play for the wrong school.
Yeah, my bad, your decision, okay. So, torque
Finally.
equals force times
Distance.
radius,
Oh,
Wrong.
my bad.
okay? So it's technically written as torque equals Fr. So if you look on your equation sheet, where's it at? What you have on your sheet is torque equals Fr sine theta.
And it is.
Typically, we don't worry about the sine theta part, and here's the reason why. So let's look at a situation like this. Shall we? So
Changing.
I'm going to take a 50-gram mass, and I'm going to put that way out here. Okay? So what's happening is that this is creating a torque. So typically when you talk about torque, you talk about what's called clockwise torque and counterclockwise torque. So from your perspective, okay, this weight out here is pulling down. So that's why this is a product of two things. It's a product of force, how much force there is, and the distance from the pivot point. So right now, when you look at that sine theta part, so what's the sine of 90 degrees?
1.
Oh,
0 or 1, because there's a big difference
It's
between
one.
oh,
two.
it's one. Oh, my
Sine of 90 is
1.
1. So if this is at a right angle
Oh, dude.
to the board, this is why we don't worry about it. Now, if I'm like pushing down at an angle like this, then, whoa, come back here.
And it
Falls
moves
off.
away.
Then it falls off and you have to worry about it. Okay? So, but unless you're given an angle, you don't have to worry about the angle part of it. So this is creating a counterclockwise torque. If I move it over here, then it's going to be creating a
Clockwise, dude.
clockwise torque, because then it's going to want to spin it like in this direction. So here's what I want to do. I want to balance this thing out. Okay, so I'm going to lock this in place. So I'm going to have this right here. So here's my question. I want to balance this out, so this is in harmony. Okay?
20.
Do I want to put a smaller mass over here?
Yeah, but not that small.
Or do I want to put a bigger mass over there?
Bigger mass.
Oh, shoot.
Bigger mass.
Why bigger?
Because it has less distance.
That's less distance, so to compensate that for, we have to have
More force.
more force. So if I put this over here,
It's not gonna stay.
okay,
Whoa, what are you doing?
and we can do a little bit of adjustment here.
It's not a pivot at all. Stay.
It's not gonna stay.
Push it there.
The miracle of modern physics.
Yup.
Now, this is a 50-gram mass, that's a 200-gram mass. What do you think the ratio is between the distances then?
1 to 4.
Exactly. So you notice that this distance is about 1/4 that of
That one.
that distance. Okay? So if you were to talk about units, what units is force measured in? Newtons. Radius is measured in meters. So torque is measured in Newton meters. So if you've ever dealt with horsepower, okay, or transmissions or seen truck commercials, they'll talk about in the English system, instead of Newton meters, it's measured in foot-pounds of torque. Okay, so foot-pounds of torque means the same thing as Newton meters. Okay, so it's just whichever system that you measure. Now, so this is where I told you you've dealt with torque every day of your life. So give that, you can just spin that whole record player. So here's the deal. I'm going to open up this door. Okay. I can do this one of two ways.
It says
I can either push here, or I can push right here. Those are my two options. Push here, push here. In which case do I need to generate more torque?
The inside.
Outside, inside, or do I generate, is the torque the same?
No, closer to the hinges will be more.
Torque is the same.
Torque is the same, why?
Because, it just is, like the radius is changing, so the amount of force is what changes on the torque.
Yeah, I've got to get this door to open.
Yeah.
Torque is gonna stay the same. Now, why is it easier out here?
Because it's
Less force.
more radius.
So with a bigger radius, I have to supply
Less force.
less force, okay? So I can push on this, okay? As a matter of fact, I can just go, take my finger and go, doink, just like this. Now, I can open it here, but what's gonna happen?
You're gonna have to try really hard.
Yeah, I gotta try really, really hard. So I can open it,
You wanna see?
but I gotta push really, really hard, okay? So in both situations,
Use a finger.
whether I'm out here or here, I have the exact same torque. This is just much harder to do because it's smaller,
Radius.
so therefore I have to have a lot more
Force.
So I can do that, but it's just tough to do. So every time you've opened up your car door, every time you've opened up a cabinet, so when you look at a cabinet design, so here's the cabinets in your house, right? So if you didn't understand physics, and here's like the hinges, right? If you didn't understand physics, you might be cool. Hey, let's put the handles right here. Okay? Cool. Looks cool. What's the problem?
It's really hard to open.
It'd be really, really tough to open. Now, if you have little kids, you want to kid-proof your house, move the handles out by the hinges. Skippy's not going to be able to pull on that, unless Skippy gets clever and goes, "Screw you! I'm not going to use the handle." And then he puts his hand underneath there and just, pulls it out like that. Okay. But this is why you look at your car door. You look at cabinet handles. This is why we put the handles far from radius. It isn't that we need more torque. It's the same amount of torque. It just makes it much easier. Okay? Got that idea? So when you look at something that's going to balance, okay? So there's a couple of ways you can think about this. So let's say we're going to have a seesaw. And be careful how you answer this. I'm going to sit on one side, and Jackson's going to sit on the other side. And we want to balance. Okay? And the fulcrum is in the middle. We want to balance. So what's going to happen?
You have to move towards the middle.
I've got to sit
Towards the middle.
closer to the middle. Jackson has to sit
On the
As
edge.
far away.
on the outside. So that's one scenario. Now, what if we had this scenario? So imagine this is me out here,
We have to get two Jacksons.
okay? No. And Jackson's here. But we can change the fulcrum.
Okay.
So we can change where it balances.
Well, wouldn't the
Fulcrum.
Move you closer to the fulcrum.
Yeah.
So would we want to go this way,
Yes.
or would we want to go this way?
No.
This way.
To
This
our,
way?
Our left,
Why?
because less radius and
Because it's
bigger
balancing.
It balances.
Okay?
Man, you just moved the whole seesaw when you could have just.
So now we could balance it this way. Now, an interesting thing happens. This actually is somewhat, and you're going to go, what does this have to do with Lagrange points? So here's the deal. So if I know the total length, just like we did the total length to the moon, so if I know this distance, what's going to be left over? Total distance minus this. So if the total length is 40 centimeters, and this is 10 centimeters,
You got 30.
that's got to be 30 centimeters. Keep that in mind. Okay, so stop that for a second.
Beep.
Okay, so up here at the top, all I did was basically give you the variables and that relationship. Here's your connecting equations that allow you to go from linear to angular. Now, here's what I want you to notice down here. Here's your linear equations that you all are used to dealing with. That equation, x equals 1/2 at squared. So notice that you can rewrite every linear equation It has the exact same mathematical form, you just put in the corresponding variables. So instead of that equation being v squared equals v naught squared plus 2ad,
Butt squared plus.
yeah, so this one you get butt squared equals butt naught squared plus 2 alpha theta, okay, or 2 fish theta, okay? So mathematically, they're treated the exact same way.
Two butt or not two butt?
Now, when you get to question number 1, I want to make sure everybody's cool with what's going to happen on question number 1. If the tip of a watch is 12 millimeters from the axis, what is the linear velocity at the tip? Okay, so imagine this. Here's my watch, okay? And this is actually off of my watch. So there's the length of my second hand, 12 millimeters. So what I want to know is, and there's a couple of ways you can think about this. One option is, imagine that you have a little radar gun and you're going to shoot it at the end of that second hand, and you want to know what the radar gun is going to show. That's one way to think about it. The other way you can think about it is that imagine that you shrink yourself down and you're inside my watch. You want to know, you want to calculate how fast you have to walk inside my watch to keep up with the end of the second hand. Okay? Now, here's the deal. What you want to do is you're going to start with the idea that here's the second hand of the watch, right? As it makes one revolution, how long is that going to take? 60 seconds, right? So that's my time. How many radians is that going to take? Or how many radians is that going to move through?
Two butt.
Two butt.
So to get omega, that's going to be theta over time, because a second hand moves at a constant rate of movement, right? We're not speeding up, we're not slowing down. That'd be really weird. So that's going to be 2 pi divided by 60 seconds. Now, when you do this, don't get cute. Don't leave it as 2 pi. Divide that out. Do not round that too much. Devin Short, you listen to me, Devin. Do not round this. I know Devin isn't here, but I'm saying that for Devin's benefit anyway.
Yeah, Devin.
Don't round it. Now, I'm not also saying write it out to 12 decimal places. Okay?
Please, please. It's gonna be 0.1. Ooh, 1.047.
So yeah, you do like what you get when you do that 0.
Point
Point 1047.
So 0.105 radians per second. Okay,
Not too good.
so that's the value of your butt.
Ooh.
So you want to figure out your linear velocity. So what are you going to do?
Worth $1.
V equals R omega. Right, Jackson?
Yeah.
Do you know the radius?
Yeah.
Now, this is where this gets weird in terms of radians floating in and out. This is going to be meters times radians per second. But when you do that, the radians like float out because it's a dimensionless number. So when you get this, don't write that answer as meter radians per second. It's just meters per second. Okay, because radians are a dimensionless number. When you get to question number 6 at the bottom, okay, so visualize this in terms of Jackson and I. You have George on one side, mass of 56 kilograms, Joe on the other, 43 kilograms, and we have a 1.75 meter
I
long
thought that's
seesaw.
radians per second.
You get to choose where you put the
Doesn't
fulcrum,
that come out to radians?
okay? Now, this is just going to be like the Lagrange problem.
E equals par.
You're going to know, here's going to be your total length, 1.75 meters. If you let one distance be x, what's left over?
Distance.
1.75
minus
minus x. So you're going to set the two torques equal to each other. This is going to be an algebra problem more than about anything. When you get to the questions in the book, okay,
What?
there are not very many of them.
Let's go.
So here's the deal. This will make sense when you go to answer these. In the book, if you have clockwise torque or movement, that's defined as negative. Counterclockwise is defined as positive, okay? So that's what that's referring to, okay? So in the book, and this is how I want those answered. Clockwise is negative, counterclockwise is positive.
Why did we decide to do clocks the wrong way?
I don't know. You're gonna hate electricity then, because we've got that completely jacked up.
Great.
When you get to number 8, you've got to sketch a angular velocity versus time graph. I've given you the graph. All I'm asking you to do is make a sketch, okay? All right, I'm done. You're on your own.